Hey friends, welcome to the YouTube channel All About Electronics. So in this video and in the upcoming videos, we will learn about the feedback amplifier. And in this specific video, we will see that what is feedback, the types of feedback, and the importance of the negative feedback in the amplifier circuits. So earlier during our discussion, we have already seen the op-amp, BJT and the MOSFET circuits with the feedback. But here, we will understand the concept of the feedback in more detail. And we will also see the effect of the feedback on the amplifier circuit. And in the upcoming videos, we will also learn about the different feedback topologies. But here, first let us understand what is feedback. So in the feedback, the fraction of the output signal is sampled and then it is given back to the input side. So basically, this fraction of the output signal is either added or subtracted from the source signal, and then it is given as an input to the circuit. So depending on whether this feedback signal is added or subtracted from the source signal, we can have the two types of feedback. So if the sampled signal is subtracted from the source signal, then we will have the negative feedback. So this type of feedback is mainly used in the amplifier circuits as well as in the many control circuits to improve the stability. On the other hand, if this feedback signal is added with the source signal, then this is called the positive feedback. Because in this case if you see, then the new input to the circuit is more than the source signal. So gradually if you see, then the output signal of the circuit will increase. And that is why this type of feedback is called the positive feedback. So this positive feedback is mainly used in the oscillator and the multivibrator circuits. And apart from that, sometimes it is also used in some active filters. So here during our discussion, we will focus on the negative feedback. And mainly, we will see that how it is used in the amplifier circuits. So first, let us understand why the negative feedback is used with the amplifier circuits. Or basically, the effect of the negative feedback on the amplifier circuit. So this negative feedback desensitizes the gain of the amplifier. That means due to the temperature or some other reasons, even if the component value changes of the amplifier, then also the change in the closed loop gain of the amplifier will be minimal. Then if we see the second effect, then this negative feedback reduces the nonlinear distortion. So sometimes in the amplifier, the gain is higher when the signal level is low. And at the higher signal levels if you see, then the gain provided by the amplifier will be less. So because of that, the nonlinear distortion may arise in the amplifier circuit. So this negative feedback reduces this nonlinear distortion and it makes the gain of the amplifier almost constant. That means this negative feedback makes the gain of the amplifier independent of the signal level. Apart from that, this negative feedback also reduces the effect of the noise or the interference on the amplifier circuit. So that is the another advantage of the negative feedback. Moreover, depending on the feedback topology, it also modifies the input and the output impedance of the amplifier. And lastly, it also increases the bandwidth of the amplifier. So all these are the desirable effects of the negative feedback on the amplifier circuit. So of course, using the negative feedback, we can get all these benefits, but at the cost of the reduction of the overall gain of the amplifier. That means with the negative feedback, the overall gain of the amplifier will reduce. So now, let us see the general structure of the feedback amplifier and let us understand because of the negative feedback by what factor the gain of the amplifier reduces. So this is the signal flow diagram of the basic feedback amplifier. So here, the sampled signal can be a current or the voltage. And similarly, the signal which is sent back to the input side can also be a current or the voltage. So that is why instead of showing the currents and the voltages, here all the inputs and outputs as well as the feedback signals are represented by the X. So here this A represents the open loop gain of the amplifier and this X0 represents the output of the amplifier. So as you can see, this output signal goes to the load as well as the feedback network. So through the feedback network, a fraction of the output signal is sampled. So here, this XF represents the feedback signal. So mathematically, we can say that this XF is equal to this beta times X0. where this beta is equal to feedback factor. So here this feedback factor shows us what fraction of the output signal is fed back to the input side. So here if this beta is equal to 0.1, it means that the 10% of the output signal is fed back to the input side. So here this feedback signal XF is subtracted from the source signal and the difference between them is equal to Xi. That is the input to the basic amplifier. So here we can say that this X0 is equal to A times Xi, and here this input Xi is equal to Xs minus Xf. That is the difference between the source signal and the feedback signal. So here basically we want to find out what is the overall gain of the amplifier with the feedback. So basically here we want to find out this X0 divided by Xs. So if there is no feedback in the circuit, then as you can see this Xi is equal to Xs. That means the input to the basic amplifier is same as the source signal. And in this case this X0 divided by Xs is equal to A. That is the open loop gain of the amplifier. But here with the feedback, let us find out the value of this X0 divided by Xs. So here as you can see this X0 is equal to A times Xi. So we can say that this Xi is equal to X0 divided by A, and likewise this Xf is equal to beta times X0. So we can say that this X0 divided by A is equal to Xs minus this beta times X0, or we can say that this X0 divided by A plus beta times X0 is equal to Xs. And if we take the X0 common and if we rearrange the expression, then further we can say that this X0 divided by Xs is equal to A divided by 1 plus A beta, where the A is the open loop gain of the amplifier and this beta is the feedback factor. So here this X0 divided by Xs is the gain of the amplifier with the feedback, or simply it is represented as the AF. So without the feedback, the gain of the amplifier is equal to A. But with the feedback, as you can see, it will reduce by this factor, that is 1 plus A beta. So here this A beta is known as the loop gain, and for the negative feedback this A beta should be positive. That means if this A beta is positive, then this feedback signal XF and the source signal will have the same sign. So whenever they are subtracted, then this difference signal will be smaller than the Xs. And that is why, because of this negative feedback, this closed loop gain AF is smaller than the open loop gain. And as you can see, it will be lesser than the open loop gain by the factor of 1 plus A beta. So here, this 1 plus A beta is known as the amount of feedback in the feedback circuit. So whenever this loop gain A beta is much greater than 1, then this closed loop gain AF can be approximately written as A divided by A beta, or simply we can say that it is equal to 1 divided by beta. That means whenever this loop gain A beta is much greater than 1, then this closed loop gain is almost independent of the open loop gain. And in that case, it can be entirely determined by the feedback network. So typically, this feedback network consists of the passive elements, and that is why it is possible to select the precise value of these components. Or in a way we can say that it is easy to set the gain of the feedback amplifier. So for example, as you know, when the op-amp is used in the closed loop configuration, then just by using the external resistors, it is possible to set the gain of the op-amp, right? Well, that is actually possible because if you see the open loop gain of the op-amp, then that is very high. And that is why when the op-amp is used in the negative feedback, then just by using the few resistors, it is possible to set the gain of the op-amp. Alright, so let us see the another interesting thing related to the feedback. So with the feedback, we have seen that the closed loop gain AF is equal to A divided by 1 plus A beta. Or from this we can say that this X0 is equal to A divided by 1 plus A beta times Xs. Now here we know that this feedback signal XF is equal to beta times X0. And here the value of X0 can be given by this expression. So further we can say that this feedback signal xf is equal to A beta divided by 1 plus A beta times xs. So here, if this A beta is much greater than 1, then we can say that this feedback signal xf is almost same as the source signal. That means if the loop gain A beta is much greater than 1, then this feedback signal xf is almost identical to the source signal. And because of that, the difference between them is almost 0. That means if the loop gain is very large, then the inputs appearing at the comparator or at the mixer circuit are almost identical. And the same thing we have also observed in the op-amp circuit. That means whenever the op-amp is used in the closed loop configuration, then we can apply the concept of the virtual ground or the virtual short. And we can assume that the inputs which are appearing at both the input terminals of the op-amp are almost identical. So this holds true whenever the loop gain of the op-amp circuit is very high. And in most of the cases, that is also fairly true. So now, let us take the example of an op-amp circuit and let us understand the concept of the virtual ground or the virtual short from the perspective of the feedback amplifier. And let us also understand how the gain of the op-amp can be set just by using the few external components. So here, we are taking the example of the non-inverting amplifier, where this Vs signal is applied at the non-inverting terminal of the op-amp. So here, let's say the voltage at the inverting and the non-inverting terminals of the op-amp are V minus and the V plus. So here, the same circuit can also be drawn like this. So as you can see, here this non-inverting terminal is shown at the top side. So here, this R2 is the feedback resistor and the R1 is the resistor between the inverting terminal and the ground. So here, we are assuming that the op-amp is the ideal op-amp and here, no current is flowing into the op-amp terminals. So in reality, the op-amp will provide the very high input impedance and only a very small current will flow into the op-amp terminals. But here during our analysis, we can assume that the input terminals of the op-amp does not draw any current. So in that case, if you see, then from the output node, the current will flow through this resistor R1 and the R2. And just using the voltage divider rule, we can find the voltage across this R1. Because here, if you see the voltage across the R1, then that is the feedback voltage which is going back to the inverting terminal. And as you can see, it will get subtracted from this source signal. So here, we can say that this feedback voltage Vf is equal to R1 divided by R1 plus R2 times V0. And the same voltage will also appear at this inverting terminal. So we can say that this V minus is same as the Vf. And here, since the Vs is connected to the non-inverting terminal, so we can say that this V plus is equal to Vs. So here, if the loop gain of the op-amp is very high, or in other words, if this A beta is much greater than 1, then we can assume that this V plus is approximately equal to V minus. That means the feedback signal Vf is almost same as the source signal. So let us put some numbers and let us understand why it is true. So we know that the closed loop gain of the op-amp or this Vout divided by Vs can be given as A divided by 1 plus A beta, or we can say that this Vout is equal to A divided by 1 plus A beta times Vs, where this A is the open loop gain of the op-amp and the beta is the feedback factor. So here, let's say the open loop gain of the op-amp is equal to 10 to the power 6. And as I said earlier, this feedback factor represents what fraction of the output voltage is feedback to the input side. So in this case, as you can see, that is the voltage across the resistor R1. Or we can say that the feedback factor beta is equal to R1 divided by R1 plus R2. So let's say here this R2 is equal to 9 kilo ohm and the R1 is equal to 1 kilo ohm. So we can say that this value of beta is equal to 1 kilo ohm divided by 1 kilo ohm plus 9 kilo ohm, that is equal to 0.1. That means here this open loop gain is equal to 10 to the power 6 while the feedback factor is equal to 0.1. So here if you see the value of the A beta, then that is equal to 10 to the power 5. And as you can see, it is much larger than 1. So once again, now if you see the expression of the closed loop gain, then that is equal to A divided by 1 plus A beta. And here, since the A beta is much greater than 1, so we can say that this closed loop gain is approximately equal to 1 divided by beta, and that is equal to 10, because here this beta is equal to 0.1. Or if we see the precise value, then it is equal to 10 to the power 6 divided by 1 plus 10 to the power 5. And if you calculate the value, then that is also approximately equal to 10, and that is equal to 1 divided by beta. So here this beta is equal to R1 divided by this R1 plus R2. So if you see the value of the 1 divided by beta, then that is equal to R1 plus R2 divided by R1. Or from this we can say that the gain of the op-amp is equal to 1 plus R2 divided by R1, and that is the gain of the non-inverting configuration of the op-amp. And this equation holds true whenever the value of A beta is much greater than 1. So in such case, just using the external resistors, it is possible to set the gain of the op-amp. So similarly, when this A beta is much greater than 1, then the concept of the virtual ground or the virtual short is also applicable. For example, here this Vf is equal to beta times V0, or that is equal to A beta divided by 1 plus A beta times Vs. So here in this case if you see, then this A beta is equal to 10 to the power 5. So we can say that this feedback voltage Vf is equal to 10 to the power 5 divided by 1 plus 10 to the power 5 times Vs. And here, since the A beta is much larger than 1, so this Vf is approximately equal to Vs. Or in other words, the voltage at the inverting terminal will be same as the non-inverting terminal. But this holds true whenever this loop gain A beta is much larger than 1. So let us see what happens when this A beta is not that large enough. So let's say now the open loop gain of the op-amp is equal to 10 to the power 3. And here the feedback factor is still same. That means the value of the R2 is equal to 9 kilo ohm, while the value of R1 is equal to 1 kilo ohm. So in this case if you see, then this loop gain A beta will be equal to 100. So now if you see the closed loop gain of the op-amp, then that is equal to A divided by 1 plus A beta, and that is equal to 10 to the power 3 divided by 1 plus 100, and that is equal to 9.9. So as you can see, for the given op-amp circuit with the given resistors values, the actual gain that we are getting is equal to 9.9. But in this case also, still this A beta is much greater than 1. So this closed loop gain of the op-amp is very close to 10. But suppose if the loop gain is even lesser, then the actual closed loop gain of the op-amp will be little off from the approximation. For example, if the open loop gain of the op-amp is equal to 100 and the feedback factor is equal to 0.1, then in that case, this A beta is equal to 10. So in that case, if we see the closed loop gain, then that is equal to A divided by 1 plus A beta. Then that is equal to 100 divided by 1 plus 10. And if you calculate the value, then that is equal to 9.09. So as you can see, now instead of getting the gain of 10, the actual gain that we are getting is equal to 9. And as you can see, it is little off from the expression. So in general, with the non-inverting configuration of the op-amp, its closed loop gain can be given as 1 plus this R2 divided by R1. And with these values, it should be equal to 10. But here, since the open loop gain of the op-amp is very less, so the actual closed loop gain that we are getting is equal to 9. That means whenever this loop gain A beta is much greater than 1, then and then only this closed loop gain entirely depends on the feedback network. Moreover, in the op-amp circuits, whenever this A beta is much greater than 1, then and then only the concept of the virtual ground or the virtual short is applicable. For example, if this A is equal to 100 and the beta is equal to 0.1, then once again this A beta is equal to 10. And in that case, if we see the feedback voltage, then that is equal to 0.9 times Vs. For example, if the source voltage Vs is equal to 2 volt, then the VF will be equal to 1.8 volt. That means in that case, the voltage at the inverting terminal will be 1.8 volt, while the voltage at the non-inverting terminal will be equal to 2 volt. And as you can see, in this case, this V plus is not same as the V minus. That means here, the concept of the virtual short does not hold true. So this concept is valid when this loop gain A beta is much greater than 1. So that is the basic overview of the negative feedback and the effect of that on the feedback amplifier. So in the next video, through a mathematical analysis, we will understand these effects in more detail. Like we will see that how this feedback desensitizes the gain and how it reduces the nonlinear distortion. So that's it for this video, and I hope in this video you understood the basic concept of the negative feedback. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.